See, these are the components for the Hall effect experiment. This one is the electromagnet. These three are related to the DC power supply, which is connected to the electromagnet to produce the magnetic field. Digital gas meter to measure the magnetic field. Hall effect experimental setup to measure the voltage and the current of a given semiconductor. This is the stand used to place the semiconductor in between the electromagnet. Coming to the Hall effect point of view, Hall effect is nothing but once a current carrying semiconductor, the conductor is placed in a transverse magnetic field, Hall voltage is generated across the semiconductor. That voltage is measured across the semiconductor by giving the different current values. This is the experimental motto to measure the current and voltage of a particular semiconductor. First, in this, we need to give the power connections to the electromagnet to generate the magnetic field, as we are placing the semiconductor in the transverse magnetic field. For this, the power connections need to give for the input of the electromagnet so that it can generate the magnetic field. The power connections are as follows. This is the power cable used for the connection setup for the electromagnet. There is the red is like a positive and black is like a negative. Just given the positive connections to the positive and negative to the negative of the electromagnet input. And the other end of the connections is given to the DC power supply. Right. Now, we successfully connected the DC power supply to the electromagnet. Once the power is on, by giving the current value, there is a possibility to generate the magnetic field in between the electromagnet coils. One is act like a north and one is act like a south. Now, the magnetic field is established successfully by electromagnet by giving the some current values. So, if you want to increase the magnetic field generated by the electromagnetic coils, we can increase the current values, or by decreasing the current values, there is a possibility to decrease the magnetic field across the electromagnetic coils. But we don't know how much magnetic field is generated by the electromagnetic coils. That part we need to measure, because in the Hall effect experimental setup, we are placing the magnetic field value in particular formula. Because we are doing the experiment in particular magnetic field environment, then definitely we should measure the magnetic field value across the magnetic coils. For this is the sensor to measure the magnetic field. This sensor need to place between the electromagnet coils, and other end of the sensor is need to give for the gas meter. So the purpose of gas meter is to measure the magnetic field value. See, the other end of the sensor is given to the gas meter. Now the gas meter is in on position. It's showing some value. By placing the sensor between these two, it's showing the negative value. That it means that the sensor need to be reverse it. Now it is showing some value like 0.190, or it's around 0.2 gas. So that value can be changed by increasing the current value. See, the sensor is placed here using the stand, and this is the magnetic field value 0.205 and by supplying the power value is 0.54. Now I slowly increase the current values. Similarly, the magnetic field is also changes. I just fix the magnetic field up to 1 kilogauss. I'll note down the value of 1 kilogauss. Here we are doing the experiment in 1 kilogauss magnetic field environment. Now the measurement of the magnetic field across the electromagnetic coil setup is also over. The step 1, we just give in the power connection. The second one, we just measure the how much magnetic field is generated. Now we can turn off the gas meter. Even we can remove the sensor without disturbing the power supply value. Now this is the time to place the semiconductor between the electromagnetic coils. This is the semiconductor. This need to be placed between the coils. Once it is placed, the other end of the semiconductor coils need to give for the measurement of the voltage and the current setup. Semiconductor is placed between the electromagnetic coils using stand. Other end is connected to the voltage and current setup. See here, the connections are given. Now the initial current and voltage value of the given semiconductor is showing 0 and 0. According to the Hall effect experiment. So once a current carrying semiconductor is placed in a transverse magnetic field, Hall voltage is generated. Here the current is 0. Now we are placing the semiconductor in the magnetic field, transverse magnetic field, but the current is 0. That it means that there is no voltage is generated. So according to the Hall effect principle, once the current carrying semiconductor, then only voltage is generated. Now we are applying the current value across the semiconductor. Current increases, voltage also increases. So our aim is to measure the relation between the current and voltage. Note down all the values of both the current and voltage in a tabular column by taking the current in one column as input and voltage is the other column, from lowest values to the highest values. This is the experiment related to the Hall effect. After measuring both the current and voltage values, we should draw a graph. By using that graph, we are measuring the Hall coefficient value, carrier concentration, mobility, etc. The procedure to draw the graph and the measurement of other parameters is discussed in continuation video. These are the measured values of the current and voltage in milliamps and the millivolt, and the applied magnetic field in the applied magnetic field environment 1 kilogauss, which is equivalent to 10 power 3 gauss or 0.1 Tesla. This applied magnetic field you can choose based on your option. Here I chosen the environment is 1 kilogauss magnetic field environment. By measuring all these values, take the graph like voltage is on y-axis and the current is on y-axis, voltage is on x-axis. There is some uncertainty in the positions. Just try to fit the curve, linear curve. By fitting that curve, measure the slope. The slope gives the delta y, delta I by delta v. This slope gives the information of the delta I by delta v value, which is used to measure for the Hall coefficient. So the same value is substituted in the formula of Hall coefficient measurement. Coming to the Hall coefficient formula, it is derived based on the theory VH by I into Z by B, V by I is taken as average from the graph. That is, in the slope value gives the delta I by V, but in the formula we require of V by I, which is nothing but 1 by slope. Here the Z is nothing but thickness of the given semiconductor. Here we taken the thickness is 0.7 mm. It should convert into the meters, 0.7 into 10 power minus 3 meter, and B is the magnetic field. Already we discussed this value is 0.1 Tesla. So by substituting all these values, we can able to calculate the Hall coefficient. The result, if it is positive, that gives information about the p-type semiconductor. If the result is negative, that gives information about the n-type semiconductor. That means Hall coefficient gives the information about the nature of the semiconductor. If it is positive p-type and negative n-type. Coming to the other parameter like carrier density. Carrier density means how many electrons are present in the semiconductor or how many holes are present in the semiconductor. The formula is carrier density is nothing but, in general, Hall coefficient value is nothing but RH is 1 by Ne. N is the charge carrier concentration. Once you've taken the N is the formula which is equivalent to 1 by RH into E. RH is the measured Hall coefficient. This Hall coefficient which is equal to the 1 by Ne. By using that formula, here the E is nothing but 1.6 into 10 power minus 19 coulomb. By substituting the measured Hall coefficient value and the charge value, there is a possibility to measure the carrier density. And then carrier mobility. Mobility is nothing but, as we know that sigma equivalents to Ne mu. Mu equivalents to sigma by Ne, but 1 by Ne is nothing but RH. So by substituting the conductivity and the measured Hall coefficient value, conductivity is already given parameter which is equivalent to 0.4713201. So that value and the measured Hall coefficient value is used to measure the carrier mobility. By using this Hall effect setup, we can able to measure the nature of the semiconductor by knowing its Hall coefficient. By measuring the Hall coefficient value, there is a possibility to measure the density and mobility.